is by Allan. The next talk is by Allan Berele from DePaul, and he'll talk about specialized symmetric polynomials.
Thank you. Well, first of all, I'm very sorry that I can't start my talk off by saying how happy I am to be here in Israel at the conference. But I am happy to be here, and I want to thank the organizers for honoring Amitai and Alon with this lovely conference and honoring me by inviting me to speak at it. When I was a graduate student at University of Chicago, I got interested in PI algebras. My advisor, Yitz Herstein, sent me to Israel to work with Amitai. Now, everybody knows what a great mathematician and teacher and many other things Yitz was. It turned out he was also a good shadchan, a good matchmaker, and because Amitai was a wonderful advisor for me, and we continued to collaborate and wrote many papers together. Two very short stories about my time at Weizmann before I start on my talk. The first one is one I have never told anyone before, and when you hear why, you'll know why, because it's very embarrassing. When I first started to work with Amitai, he gave me a problem to work on. As you may know, Amitai had used the representation theory of the symmetric group to study multilinear polynomial identities, and he suggested that I should try to do something similar using a general linear group to study homogeneous polynomial identities. And when he first showed me that problem, my thought was, what for? Why would anybody want to do that? Could there possibly be any interesting information there? But I was really smart because I trusted Amitai. And it turned out that not only did that turn into my thesis, it turned out to be one of my best known works. So trusting Amitai was a good idea. So Amitai did many things to help me get started on my thesis. And one thing he did was he organized a seminar in representation theory. And there were 3 people at the seminar, Amitai, Delon, and myself. And here's how we run the seminar. First, Amitai or I would present some theorem in representations of the symmetric group, the general linear group, symmetric functions. And if we're finished, Delon would jump up, very enthusiastically, of course, and say, well, wait, it has a combinatorial proof. And that's how I learned combinatorics. So together, my 2 teachers are turned 150. So instead of wishing you Admei B'Esrim Shana, I have to wish you Amatayim V'Arba'im Shana. Okay. Anyway, it turned out in the past year or so, I did some work in one of those rare subjects, which is the intersection of combinatorics and PI algebras. And it seemed to be an ideal thing to talk about since we have people here in combinatorics and we have people here in algebra. This is joint work with my colleague, Stefan Catoyo, and for reasons that unfortunately will become clear, no comments until slide number 13. Okay. I think to advance the slide. There it goes. So, okay. So since I'm speaking to a mixed company, let me define a quick review of classical symmetric function theory. So a symmetric polynomial in variables is one that if you commute the variables, it is invariant. For example, x1 plus x2, x1 times x2, x1 squared plus x2 squared. A symmetric function is an analogous object in infinitely many variables. You allow infinite sums of variables, but you don't allow infinitely many variables to be multiplied together. It has a technical definition, which I am not going to read for you. Anyway, there's 4 famous classes of symmetric functions, corresponding to symmetric polynomials. The first are the elementary symmetric functions, E for elementary. E sub n is the sum of all products of n distinct variables. And for any partition lambda, E sub lambda is the product of E sub the parts of the partition. These are all symmetric. The complete symmetric functions are very similar, except now we allow equalities. So Hn is the sum of all degree n monomials. And again, for any partition, H sub lambda is the product of the H sub lambda i's. See, slides go fast. The power symmetric functions, Pn is the sum of the nth powers of the variables. And for each partition, you can guess it by now, P lambda is the product of the P lambda I I should just comment that these guys here are important because you use them when you're studying the characters of the symmetric group. The last ones are perhaps the most beautiful, but they're also a tad more complicated. They're the short functions. They have several definitions. You can define them using the determinant of the elementary symmetric functions, the determinant of the complete symmetric functions. They have an even nicer definition using semi-standard Young tableau. In the interest of keeping things light, I will not bother with the definitions. If the number of variables is infinite, then each of the sets E lambda, H lambda, P lambda, and S lambda give a basis for the ring of symmetric functions. In each of the sets En, Hn, and Pn is an algebraically independent set of generators. I didn't write down Sn because Sn is actually equal to Hn, so it's true but redundant. And you will not be surprised to hear there are many interesting algebraic relations between these functions. You can see McDonald's book about that. And as Delon taught me, many of them have very, very nice combinatorial proofs. Okay, what if instead of doing symmetric functions, we do symmetric polynomials? What if there's only finitely many variables? So a nice example to look at are the elementary symmetric functions. So En is the product of all n distinct, in this case, y's. So if there aren't n distinct y's, then En is 0. So obviously we have relations. Slightly less obviously, it might be due to Sir Isaac Newton. E1 through Ek, if there's k variables, are still algebraically independent. They generate the ring of symmetric polynomials. So the relations En is 0 whenever n is bigger than k generate all relations among the elementary symmetric functions. And the E lambda, where lambda is restricted to have all parts less or equal to k, have a basis for all symmetric, for the space of symmetric polynomials. And you can get relations among other symmetric functions using the change of basis from the elementary to the other ones. It's not a big deal. An important special case is the short functions, where we have S lambda is 0, if and only if the partition has more than k parts, and the other ones form a basis. Okay, good. And then we come to specializations. Let's say we have n variables, y1 through yn, and we're given d1 plus dk is equal to n, and we can specialize. The first d1 variables go to x1, the next d2 variables go to dx2, and so forth. And I'll denote the specializations with the superscript d whenever I remember to. So if d is 3, 1, then Pn, which is y1 to the n, y2 to the n, y3 to the n, y4 to the n, when you specialize it, the first 3 become equal. You get 3x1 to the n plus x2 to the n. En, well, here's E3, and the way it specializes is the first one specializes to x1 cubed, the next 3 terms specialize to x1 squared x2, and there's an example for Hn. Obviously, these guys are not symmetric, so calling them specialized symmetric polynomials is not a wonderful name, but they're symmetric polynomials that have been specialized. Okay. And here's the general formulas. They're not very deep. They're just what you imagine. Pi is the easiest. You just give each of the xi's a weighting factor. And for the E and the H, you have to count how many ways there are to choose I things from di things, either with or without repetition. Okay. And here's the thing I find was really cool when I figured it out. These formulas make sense even if the di are not positive, even if they're not integers, even if they're not real. I can use the formulas from the previous slide to define specialized symmetric polynomials for any di. Technical point, I always take the di to be non-zero, not everyone does. You could also define the S lambda upper d, any d, using either the tableau definition or the determinant definition. Since I haven't defined the short functions, I'm not going to bother doing that. And all the relations between McDonald's book that hold between the classical symmetric functions, meaning infinitely many variables, continue to hold among these specializations. And the main question I want to study is, what are the algebraic relations among the specialized symmetric polynomials? Okay, otherwise unknown ones. So for example, the P lambda in infinitely many variables linearly independent. So if I could find any linear relations among the P lambda, that would be an example. The problem is not solved. I have some results. and there's lots of work to be done on it if you want to. Okay, this is slide number 13. At this point, as soon as I read what's on this slide, you may make comments. Using the language of plethisms or plethistic substitution, or the language of the lambda calculus, if D is D1 to the M, D1 to the M1 does not mean an exponent, it means multiplicity, it means D1 repeated M1 times. So if D is written in this active form, then E lambda upper D can be written in terms of, as I say, plethistic substitution. In fact, all we can, using the alphabet, D1 times X upper 1 plus up to dk X upper K, where each X upper I is a set of Mi variables. Well, I don't know, when you see that slide, it probably doesn't make you sad. It simply says that my constructions can easily be expressed in this language. It's a special case of it. Maybe it gives additional insight into the construction. Doesn't seem so sad to you, I'm sure. What's sad to me is what happened just last week. I got a referee's report who rejected the paper because in my paper I didn't say that. And because he thought my constructions weren't really novel. So I been spending the last week studying plethistic substitutions as diligently as I possibly could to see if any of my theorems were already known besides the stuff that came now, which is up to now, which in a way is trivial. I found one which I'll show you, and I will dearly appreciate it if anybody sees anything else of mine, which is already known, that you tell me, because I have no interest in stealing anyone's work. Okay, anyway, so here's some examples of relations. If D1 plus up to dk is n, if they're all integers, then E m upper D is 0 for n bigger than n. If n is not an integer, then the E m upper D are not 0. Okay, let's take this, one of the simplest cases. D is D1, D2. Then here's two examples of identities you have among.
Hey, Allan, it's okay to ask a question?
Yes, that was slide 13, so you're free to ask now.
Okay, so
I just didn't want to ask I didn't want anybody to jump up and say, why aren't you using plethism before I got there? That was all.
okay, no, it's really interesting. But so you developed a translation. You developed a theory, but then the referee pointed out that it's special case of a plethism, something?
Yes, which meant that the construction is not novel, which I have to admit it isn't. But I think
maybe it's a new approach or comment.
I think the questions I ask and the theorems I prove are mostly completely novel. But
Yeah.
maybe you didn't read that far.
But the approach may be new, right?
Maybe. Took me
Yeah,
6 months to figure this out. Anyway. Okay. At any rate, if anybody, look, I'm pretty poor at programming, but even I can program these guys. Here's two identities that hold in the D1, D2 case. And if you look at it for just a sec, you'll see a very basic difference between these two. The first one has D's all over the place, and the second one doesn't. So let's make a definition. Identities which depend on K, but not on the individual D's, I will call absolute identities. And I did most of my computations using the P lambda because they're easier to program. And I know what you're thinking. You're thinking, well, even in the classical case, if you want to get to find relations between the P's, they look much messier than between the E's or the S's.
So Allan, you mean equal 0?
Yes, of course. I'm a PI guy.
Okay.
Yes, of course. So in case you're thinking that things will work out nicer for the E's or the S's, they might, but here's what I got when I found the lowest degree identities for the E's and the S's for D having two parts. And, they're interesting, but I don't see, well, anyway, maybe if you play with them some more, they will generalize, but I don't see how. Okay. Another thought I had, which I really did not explore, which might be very interesting, is a field dependence. So I almost always assume that the DI lie in the base field, but you could be more general. So if you're given two fields, a smaller field and an extension field, you could assume that the DI are in the bigger field, and as for identities with coefficients in the smaller field. For example, if D1, D2 is a square root of 2, 1, then here's an identity with coefficients in the smaller field of the rational numbers. It's not an absolute identity because if the square root of 2 was a square root of 3 or whatever, it wouldn't hold anymore. And This gives us some insight into absolute identities because you could take the DI to be algebraically independent over F, and ask for relations with coefficients from F, and that would give you the absolute identities. Okay. So say K has D parts, take any sequences with K plus 1 parts, and I can form this determinant, and I get this absolute identity. The determinant of the PAI plus BJ is 0, and it has a nice PI proof, which is as follows. Let's let that capital lambda of D be the algebra of specialized symmetric functions, and capital D upper D be the algebra of diagonal matrices with a trace with these weighting factors on it. So with respect to this trace, the trace of x to the n is P sub n upper D. Well, since the algebra of diagonal matrices is k-dimensional, we have this polynomial identity on this algebra because it's alternating k plus 1 things. So now what you do is let each xi be capital X to the AI, let each yj be capital X to the bj, and you got the proof. This theorem, this is the one thing I did find was already known. It's exercise 2.9 in Lascaux's book, and it generalizes a theorem of Belavitis from 1857. So that's certainly classical. This identity up there in bold in 2 variables, I call it CK plus 1 of XY. It's an analog of the Capelli identity in PI theory. And obviously, one variable pure trace identities in DD correspond to algebraic relations among the P lambda D. Okay. So here's some results. Remember, we thought this was known, but I don't know what the source is. Capital lambda of D has rank K, so any K plus 1 elements are algebraically dependent. If you take any K distinct integers, each of the E and I, P and I, and H and I are algebraically independent. If the DI are not in the base field, if they're algebraically dependent, the rank goes up to 2K. And based on the determinantal identity, you get this description that the specialized symmetric functions are contained in P0 up to P2K minus 1, adjoin this one inverse. Okay. So let's go to the classical case where the D's are equal to 1. Then X to the K has trace P sub K, the ordinary P sub K. And in 1996, I proved that all trace identities for diagonal matrices in any of the variables are consequences of commutativity, of course, and the Cayley-Hamilton theorem. Now, if we try to generalize to the weighted trace function, then, for example, that identity 4 slides back would translate to, so the identity starts with P5, 3, 1 translates to trace of x to 5th, trace x cubed, trace x, and so forth for the others. If the DI are all positive integers, then we're studying trace identities among block scalar matrices, which are diagonal matrices with diagonals with repeated entries. If the DI are each plus or minus 1, this case was studied by Cantor and Trishan in 1999. It's related to the theory of supersymmetric functions, which are characters of the general linearly superalgebra. And here's the theorem. All absolute identities are consequences of the determinantal identities. And I conjecture that all absolute identities for D upper D are consequences of commutativity plus the CK plus 1, the Capelli type identity. The determinantal identity of minimal degree has degree K squared plus 1, probably. And it's probably not the identity of minimal degree. An open question is, what's the degree of the minimal identity? Leopoldo Costa-Cavanagh studied the case of K is equal to 2, published in a Journal of Pure and Applied Algebra this year. They studied the mixed trace identities of D upper D1, D2. The results can be translated to symmetric polynomials to prove that all relations are consequences of these. This is actually not really a translation of the results. It's a form of their results that I proved before I saw their stuff. Let X be a generic diagonal matrix. I know that X is algebraic over the ring of specialized symmetric functions, but I don't know if it's integral. I'm thinking that if it was, this would be an analog of Cayley-Hamilton, which would certainly be very interesting. For example, for D1, D2, you have this identity here. And since D1 and D2 are in the field, I can divide by D1, D2, D1 plus B2, and get that X is algebraic over the specialized symmetric functions. I think that it's true in general. I have a conjecture about the degree. Let D be these distinct parts with multiplicities, and I conjecture that the degree should be the product of the mi plus 1, and then you subtract 1. So in our case, m1 is 1, m2 is 1, so it's 2 times 2 minus 1 is 3, which is the degree of that polynomial. And I checked it in the cases below. Let's take a closer look at this identity. If you want an identity among the p lambda, you could try taking trace of both sides. If you do, you'll get 0. So you do a pi thing. You multiply both sides by x, you take trace, and you get a relation among the p lambda.
Allan, sorry to interrupt, but can you clarify again what's a little bit lost? What's capital X? An arbitrary diagonal
matrix? An arbitrary diagonal matrix.
Okay. So that's like a Cayley-Hamilton type.
Oh,
identity.
yes, that's exactly right. That's exactly what it's supposed to be.
I'm a bit confused. If I remember correctly, the Capelli identity that I know is you have two non-commuting, like the quantum relations. And suddenly,
yes, the classical Capelli is non-commutative.
Yeah. So the Capelli you refer to, but in your case, it's all commutative, right?
So the relation between my Capelli, where the heck is it? The relation between, oh, there it was. Relationship between my Capelli and the normal Capelli is it's in two sets of variables and in k plus 1 of each, and it's alternating in one of the sets of variables. That's its analog to the Capelli.
Thank you.
Okay. Anyway, almost there. So as I say, if you multiply both sides by x and take trace, you do get a relation among the p lambda. And the interesting part is the very last term becomes the negative of p1 to the 4th power. That means that p1 is monic algebraic over f adjoint the other p's. And then using multilinearization, that implies that any product of 4 traces can be written as, with the trace being the weighted trace, can be written as a linear combination of terms with each with 3 or fewer traces, which to us algebraists is interesting. And the computations that I did support not only the conjecture about Cayley-Hamilton type equation, but also suggested that in general, P1 is monic over this, and the degree should be the product of the mi plus 1s. Okay. Finally, how much time do I have left, if any? What time am I going till? I don't want to go over and bore people. What time do I have till?
We started 5 minutes late, I think. So it's
So I have till 11:35?
yeah. 12:35.
That's fine.
11.
So now we turn to pure PI theory.
Yes, this is the last talk. It's no big deal if you go over time.
No,
Yes. Don is like,
Don Passman once said to me, the saddest words in the world are, could I have just a few more minutes? Okay, so let Xi be a generic diagonal matrix, and for each I, they'll have different entries. Their entries are algebraically independent, they're variables. And Vn is contained in the commutative algebra generated by their entries. And it's the vector space of all evaluations of all degree n, multilinear pure trace polynomials in x1 through xn. And if that doesn't make enough sense, so for V3, it'll be the span of the following 6 pure trace polynomials. And those are all, there's n factorial. If the trace is the D trace, then the dimension of the space is the nth pure trace codimension, denoted Cn of the D upper D. And if you want to go whole hog, Vn is also a module for the symmetric group. It has a character, and the character is the nth co-character of D upper D denoted with a chi. Okay. So I've proved, based on the work of Leopoldo Kostakov and Lamartine, that if D1 and D2 are distinct, then the pure trace code dimension is 2 to the n minus n. In the classical case, Cn is the number of ways to place n distinguished objects into k indistinguished boxes, some possibly empty. It's obviously related to the Stirling number of the first kind. It's asymptotic to k to the n over k factorial. And in general, I can prove that C sub n, the nth codimension, is asymptotic to some constant times k to the n, and have upper bounds and upper bound and lower bound for a. And based on not much evidence, I'm guessing that the correct value of a is 1 over the product of the mi factorial. Okay. For the trace cocharacters, well, everyone knows that the characters of the symmetric group are indexed by partitions. They're denoted chi upper lambda. Since the symmetric, by Maschke's theorem, the character can be written as a direct sum of irreducibles. So we have multiplicities m lambda for each chi lambda. We're interested in computing the n lambdas. In the classical case, the pure trace cocharacter has a number of nice descriptions computed by Amitai and myself in 1995. First of all, m lambda will be 0 if lambda has more than k parts. That's true in the twisted case. But here's a really nice algebraic description of m lambda. The for each partition lambda, there's an Sn character module, there's a GL module. You take the GLK module corresponding to lambda. And of course, the symmetric group Sk is contained in GLK as a permutation matrices. And the multiplicity ML is a dimension of the fixed space, the Sk invariance in W lambda. I've always been fond of that. There's another nice description in my paper with Amitai of the cocharacter using Poincare series, using Molian's theorem. I'm not going to talk about it because I'm going to go over. A third description is a new one. It just gives an estimate. M lambda is bounded above by the number of semi-standard tableau of shape lambda, whose type is a partition with at most k parts, and is bounded below by the number of semi-standard tableau of shape lambda, whose type is a strict partition, all parts not unequal, with at most k parts. And for d is equal to d1, d2, I have a formula. It's not super exciting. It's lambda 1 minus lambda 2, in most cases plus 1. In general, if A and B are two algebras with trace, then A plus B also has the obvious trace of adding up the trace of each. And the trace cocharacter has this bound that chi n of A plus B is bounded by chi A of A, tensor chi n minus I of B. That's the outer tensor product is computed by Littlewood-Richardson rule. And just for short, I'll write chi of A plus B is bounded by chi of A tensor chi of B. So in our case, where D is D1 to the M1, okay, I'll try to finish up real soon. Then the D is a direct sum of those guys, and each one of those is independent of D, and the cocharacter is the same as classical case dm. So that gives the upper bound, which gives the upper bound dimension. We have a lower bound also. I think that's it, isn't it? Good. Thank you so much for coming to my talk. Happy birthday to Amitai and Delon, and thank you for everything.
So you talked about a lot of interesting stuff. So you say it's a sad story. So according to the referee, everything you talked about is already known?
No, up until slide 13. Up until slide 13, everything is known.
Oh, so the sad part is only in the beginning.
Yes.
Okay, that's nice. So the happy ending. Okay.
Well, it's not every. I still have to find another journal and submit it and add a paragraph and say this can also be done using the language of clothestic substitutions and the reference to the 1832 paper of whatever his name was.
So do you have more with a specialized thing? Can you do it for the other fancier stuff, like here Hall polynomials and even McDonald polynomials? The specialized operation.
As I'm sure you know, Devon, the most general theory of clothestic substitution is you have a symmetric function and you substitute it into a quasi-symmetric function.
Ah.
And this has certainly been used by people like, my mind is going, to study, you know, like the QT McDonald polynomials and things like that, and prove all sorts. I think Jeff Remmel did that, and a lot of other people. Garcia, Heyman, I don't remember who all, but yeah.
Okay.
Statistic substitutions, you know, are very popular among some people. One of whom was my referee, I'm sure.
Okay.
Well, now I get to say that these results, the results in slide 13 on have to be new because I presented it to 67 people and nobody else said anything else was known.
Well, thanks for reminding me about the small seminar we had way back in the good old days.
Oh, I have very fond memories of it.
Yeah, okay.
You know, it was
Yeah,
the
I
only
learned
class
so much I learned from you and from Amita. I learned so much.
it's the only course I ever took in combinatorics.
Yeah.
And it gave me a very good impression of the field.
And I learned a lot of algebra from you and Amita.
Yeah.
Question. Question.
Yeah, you are welcome to ask.
Okay. Regarding the last slide, on your last slide,
Yes.
you had a couple of bounds, and how tight are they?
Where is it? Oh, I closed it. Okay, so can I get from here? Well, in terms of, I can say that precisely. Just a sec. Oh, right here it is. Yeah, you see the side here where I give upper and lower bounds on the codimensions? Those are the dimensions of the upper bound and lower bound. So they have the same exponential behavior, and the difference between them is, I guess, the difference between k factor, well, it's k choose the mi's is the numerical difference between them.
I was referring to the very last page.
I thought I was too.
One later one. This is lower and upper bounds.
Yeah,
Here.
so you take the dimensions of the lower bound, the dimension of the upper bound, the degrees, you get those upper and lower bounds in the codimensions, which gives you kind of a precise. So the ratio of the upper bound to the lower bound looks like k factorial divided by m1 factorial up to mk factorial.
Okay.
So they have the same, you know, they're both polynomials of the same degree, but with different coefficients is the degrees. They both have the same height. I haven't done any computations of these guys yet because it's, even for two of them, will be pretty complicated. In fact, I was thinking perhaps the next test case to look at is D1 to the M1, D2 to the M2. I haven't done that case yet. It might be interesting. It might be doable, but I don't know.
Okay.
Are there any more questions? Let us thank Allan. And let us thank all the speakers for today's session. It was a great session. Thank you.
Just so, Allan, 1 to the m is the classical, no?
Yes. The
So
classic,
even this is not known. It was not studied before. The co-characters of.
Amitai and I studied the classical one.
Amita studied.
Amitai and I, we have a paper about it.
Oh, okay.
I think it's called
But
More
not in this
Cocharacters.
not in this language.
Well,
Yeah. Okay, so everyone loves to see like you're referring to see everything in his own language.
you know, it's in the Gemara.
So this-
Okay.
Yeah. So this is your 95 paper?
I think so.
Okay. Yeah. Have you been here yesterday? Yesterday, the people from enumeration of permutation pattern avoidance,
Yes.
they try to imitate your paper on super Lie algebras all their life, but the results are not so nice. So,
You know, if Amitai here, he might. I realized something the other day that I hadn't realized before. Maybe Amitai's known it for the last 40 years. Everyone knows that you can bound the code dimension of a PI algebra by counting the number of V-good permutations. And it turns out that of course, Amitai's proof shows that for n by n matrices, that the trace codimension is exactly equal to that,
yeah.
which means that you're not going to do any better than it.
Yeah. Okay. So
So
do you
the
speak? Yeah.
The K-goods give you just about everything.
Do you speak from your home, not from your office?
From my home, yes.
I say this is an Hamish meeting, Hamish workshop. Everyone,
Yeah.
this is some coffee, a cup of coffee.
So Alan, this is Sifrei Kodesh on the right hand side.
I think so. Yeah.
But you also have mess books.
I have math
It's
books
hard to
too.
see. Okay,
You know,
it's hard to
No.
see.